Now let's assume that we know the kinds of objects that we want to recover the shapes of using photometric stereo. So we know the stuff that they're actually made of. Say for instance, this object right here. It's made of plastic. We know it has a diffuse component, also seems to have some specular surface component to the reflectance. But there's no way we can take a look at this material right here and be able to write a simple expression for the bidirectional reflectance distribution function, the reflectance model of this material itself. However, we have access to the material. This is often the case with things like plastics or with paints that are sprayed on various manufactured objects. So in such cases, we can actually build an object of known shape with the same material and use it as a calibration object to apply photometric stereo to the object of unknown shape. And that's what we call calibration-based photometric stereo. This is a data-driven approach. So here you see an object right here, and it is painted with some kind of paint, a spray paint, and we don't know the BRDF of this material. So what we do is we create another object, which we'll call the calibration sphere. Sphere is a good object to use for this, and we spray it with the same paint, so you get this. So now we know that these two objects have the same reflectance properties. And we're going to illuminate these two objects with the same set of light sources. So for example, if you take a look at these two surface normals on this object right here, this one and this one, the intensities at those 2 points are going to be exactly same as the intensities on the sphere at the 2 points that have the same surface normals, right here. If you change the lighting, that remains true. Change it again, that remains true. And this is called orientation consistency. That is, if you look at it, you're looking at the same material, if you're looking at a given surface normal on the object, and you go to the sphere and you look at the same surface normal, the set of intensities produced by the point on the object should be exactly the same as the set of intensities produced at that point on the sphere with the same surface orientation. And that's the fact that we're going to use to solve the problem. So what we do is we take a set of images with the same light sources we're going to use on the object during photometric stereo. We're going to take a set of images of this calibration object. In our case, we're going to use a sphere. And the sphere, once again, has been painted with the same material, or it's made of the same material. And now we have, at each point on the sphere, corresponding to the K light sources, you have K image intensity values, I1 through IK. And now what we're going to do is take one of the images of the sphere and find the occluding boundary, the edge of the sphere. That's this circle right here. That circle tells you everything you need to know about the sphere for our purposes here. Once you have the circle, you know that you're looking at a hemisphere, and you know the radius in pixels in the image. You can go to any point on in this image right here on the sphere, and you know what the surface normal at that point is. And that gives you the surface normal map right here. So now you have a mapping between intensity values measured in these images to a surface normals on the sphere itself. So using the known size of the sphere, we calculate the surface normal PQ1 for each point on the sphere. This whole process is the calibration process. So once you've done that, you're going to create a lookup table. The index of the lookup table is really this K tuple that you have, the set of image intensity values I1 through IK. And the entry corresponding to that index is the surface orientation PQ on the right side right here. So we populate the entire lookup table with I1 through IK as the index and PQ as the entry. That's the calibration process. So now it's easy. You illuminate the object of interest with the same set of light sources, take a set of K images, and then at each point on the object, you're going to simply take the k tuple, the intensity values I1 through Ik, go in and look up your lookup table and read out the PQ value corresponding to that point. So you get a surface normal map. Very simple. As long as the calibration can be done, it's a very, very simple approach to photometric stereo.